So, why do we even measure things? Honestly, it's a great question. Why subject ourselves to finding the exact length, size, or amount of everyday objects? Why not just eyeball it and call it a day? Well, imagine trying to guess the dimensions of the support beams holding up a house. Yeah, our modern world would instantly collapse. We rely on exact measurements for pretty much every single interaction we have with the physical space around us.
Just think about the sheer distance we have to travel on a daily basis. We need to know exactly how far it is from our front door to school or to the office. We measure those endlessly long roads just to figure out how much time it's going to eat out of our day, or exactly how much fuel we need to actually get there.
And hey, it's not just about those grand distances, right? It's the totally mundane chores too. Buying a piece of cloth requires exact measurements so you don't end up short. Or think about making sure a school bag strap actually fits a tired student so they can lug around those heavy books without ruining their shoulders. Even just checking your own height or the height of a doorway so you don't smack your head. It's literally all measurement.
But then, you zoom out, and you really have to appreciate the sheer, massive scale of our surroundings. We measure the exact length of a giant football field just so we can play a game fairly. Scientists even measure the jaw-dropping dimensions of the Earth itself. Humanity is basically obsessed with sizing up our reality.
Okay, so let's try to pin our hopes on some actual structure here. Formally speaking, measurement is the process of finding the length, size, or amount of something by comparing it with a fixed known unit. And in our case, the real hero of the story is the standard unit of length, the meter. Having a fixed unit like the meter is pretty much our only way to bring order to all this chaos. It means that if I measure something on my side of the world, it means the exact same thing to you on yours.
But actually getting that measurement right, not always as simple as it looks. There are surprisingly strict steps to using a basic, everyday ruler accurately. First, you've got to position the ruler completely straight among the object, making sure the zero mark is exactly at one end. Second, you must look straight down at the mark. Third, and this is a tragically common scenario we've all faced, you have to check for a broken zero. If the zero mark is worn out or chipped off, you have to do some mental math on the fly. You start at the 1 mark instead, and then you have to remember to subtract 1 from your final reading. Finally, you read the nearest marking. And this brings us to why that second step is absolutely critical. If your eye isn't perfectly dead center straight above the mark, like if you are looking at it from an angle, you've completely ruined the measurement. It's called parallax error. It's a reading error caused entirely by your viewing angle. So, pro tip, always place your eye exactly above the point of measurement to avoid throwing everything off. But wait, just when you think you've totally mastered the straight ruler, you realize the physical world is rarely perfectly straight. Try using a rigid wooden ruler to measure the winding curves of a river or a bending path. It's impossible. A straight edge is absolutely useless when you're dealing with the beautiful, unpredictable curves of nature, or trying to measure the borders of a country on a map.
So how do we actually solve this? Well, we use the highly manual, beautifully simple thread method. Basically, to straighten out the chaotic curves of the world into a manageable line, you take a thin, non-stretchable thread, you place one end exactly at the start of the curve, you carefully bend the thread along the entire path so it matches perfectly, and you mark exactly where the curve ends on the thread. Then you simply pull that thread straight and measure it against your trusty ruler. Problem solved. Now, let's see how all this builds into our next massive challenge, motion. Because measuring stationary things is one thing, but the reality is everything around us is in constant, non-stop motion. To even begin to understand or describe how something is moving, we desperately need an anchor to make sense of it all.
And that anchor is what we call a reference point. A reference point is just a fixed object that we consider to be completely at rest. We use it to decide whether another object is actually moving and to describe its position. Think about it. We use totally stationary, unbothered things like a tree by the side of the road to judge how fast a car is speeding by, or maybe a tall lamppost to watch a cyclist ride past. Historically, humanity even used the sun itself as a massive reference point to understand the Earth's motion. The whole concept of motion only makes sense relative to a reference point. First up is circular motion. This happens when an object moves along a circular path. The absolute key here is that every single point on the moving object stays at a fixed, equal distance from a central external point. Picture a satellite endlessly orbiting the Earth, the tip of a ticking clock's second hand, a stone being whirled around on a piece of string, or even people riding on a giant Ferris wheel. That's circular motion. Next, we have rotational motion. Now, this looks kind of similar at first glance, but it's fundamentally different. This is an object spinning about a fixed line passing directly through itself, which we call its axis. Think of a wooden top spinning rapidly on the floor, the blades of an electric ceiling fan turning, or the Earth rotating on its only internal axis to give us day and night. So the crucial point here is understanding the difference between these two, because it is super easy to get them confused. In circular motion, the whole object is moving along a path around an external center, kind of like a race car driving around a circular track. But in rotational motion, the object is spinning in place around its own internal axis. This means different parts of the object are actually moving at different speeds. Basically, circular is about the path taken, while rotational is about spinning right in place. Then we have periodic motion. This is the comforting, predictable repetition of movement over equal time intervals. That repeating time frame is called its time period. A perfect example of this is the Earth's daily rotation. It reliably repeats itself, bringing us a new day exactly on schedule over and over again. It's like clockwork. Finally, we have oscillatory motion. This is a very specific type of movement, the endless to and fro, or back and forth, swinging about a fixed mean position. Imagine a kid on a playground swing kicking back and forth, a tree branch swaying heavily in a strong wind, or the strings of a guitar vibrating right after you pluck them. They move away from a central point, and they return to it repeatedly. Now, what's really fascinating here is the overlap between these last two. All oscillatory motion is inherently periodic, because that back and forth swing takes an exact equal amount of time, so a playground swing is both oscillatory and periodic. But catch this, not all periodic motion swings back and forth. The Earth spinning on its axis is periodic because it repeats in equal time, but it just keeps spinning continuously in one direction. It definitely doesn't oscillate to and fro. Think about the pendulum of a grandfather clock ticking away in the hallway. Based on what we just learned today, is that swinging pendulum's motion oscillatory, periodic, or both? Think about whether it moves back and forth, and whether it takes the exact same amount of time for each swing. I'll let you figure that one out for yourself.